Hello everybody, my name is Nathan. You've seen me before on a few other videos, hopefully. And what I want to do is give you just a quick walkthrough of the wiring and functionality of this particular VFD. So again, we're focusing on the same one. This is a Schneider product, it's an ATV31, but as I've already outlined to you guys, every manufacturer, the terminology might be, or the parameters might be a little different, but the terminology is going to be very, very similar. So we're not just focusing on one manufacturer here. This is a lab volt power supply, which you may be familiar with. And what I've done is I've wired from the fixed 208 volts, 3-phase, into the line 1, line 2, line 3 terminals of the VFD. So this is supplying power for our controller. And then that's also the 3-phase power that is then going to be rectified, filtered, and then it's going to be output through the inverter section with the use of IGBTs, because this is a pulse width modulation drive. T1, T2, and T3 are going to go down to our motor. I did wire one of the lines to a 2.5 amp analog ammeter here, so I'll show you the difference in current between no load and full load with the motor. The motor, each coil is rated for 120 volts. We have 208 volts. I'll let you do a quick thought. Should we wire this in delta or Y? Of course, we should be wiring this in a Y configuration. Our logic inputs are here. So if you'll recall, they are 24 volt logic inputs. So if I take 24 volts and jumper it here, or I go through a pilot device or switch up top, that would then make this logic input true because it's seeing 24 volts. With this lab component here, what we did is we pre-wired in all these switches. So what I'm going to do is I'm going to turn on our power here, and you'll see that we are ready. So that means we're not giving a stop command, we're not giving a run command, and there is no fault currently on the drive. And this is currently wired for, or programmed for I should say, 2-wire control. If you look in your manuals, that tells us that logic input 1 is forward, and logic input 2, or of course we can change that one, is reverse. So right now, if I go ahead and put this down right here, I am sending 24 volts to this logic input. So that should be telling the drive two things. It should be saying go, so we have to tell it to start, and it should also be saying go in the forward direction. So you may or may not be able to hear this, but this motor is not spinning. Can't register any speed here, can't visibly see any direction of rotation here, and we have an output of 0. There is 3 things that you have to tell a VFD in order to get an output, and that is go, in what direction to go in, and how fast. So for this drive, it has its own 10 volt power supply and 24 volt internal power supply. And analog input 1 is the default reference for the speed output. And that is wired to what we call a speed pot, which is nothing more than a 10,000 ohm potentiometer. And right now, this is turned all the way in the counterclockwise direction, which means I'm giving 0 volts here. Now, 0 to 10 volts corresponds to, the way I have it set here, 0 to 60 hertz. So it should make sense that we're not moving. It's doing exactly what we're telling it to do, because I'm telling it to go in the forward direction at 0 hertz. If I slowly increase this right here, now you should hear that motor spinning. Now I have an output of 25 hertz. And this will go all the way up to 60. As soon as I remove that 24 volts from logic input 1, the drive stops. So it does a small DC injection braking, stops the motor. Logic input 2 will run us in reverse. And what I'd like to do now is we are going to zoom the camera in a little bit closer down below, just so you can more accurately see the current that's drawn by the drive at no load and full load, the speed that the motor runs at no load and full load, and then actually see some rotation. So we'll see you in just a minute. Okay everybody, so I know you can't see this, but we've still got the drive up here. So I am going to turn it on. So we are going a maximum speed right now. And you can see that we are going 1,776 RPM. That would be the no load speed of this motor. And what this device also will allow me to do when I push this button is it's going to simulate full load on the motor. What I want you to notice here is we are drawing currently on the 2.5 amp scale 700 milliamps, which is in between 1/3 and 1/2 of the rated current of this motor. That is the magnetizing current drawn by this motor. So I want you to notice two things when I push this button: the change in speed and the change in current. Our current has increased to approximately 1.5 amps, which is the current rating for the coils on our motor, and the speed has dropped to 1,682 RPM, which is very, very close to the full load speed of the motor. So we can see that even through a full range, even through a full load, we can still control the speed of this motor. And you'll notice that the current is staying relatively constant, but our speed is decreasing. And if you'll recall, we talked a little bit about how the motors have little cooling fins on them. So a hazard that exists, or a consideration that exists when we're running a motor at a lower speed, is that those fan blades are not actually effectively going to keep that motor cool. So if you're running at low speeds all the time, you need some sort of extra provision for ventilation or cooling of that motor. Okay, we're going to move the camera up top now so that you can see some of the voltages. Okay, everybody, so we've dealt with the full load speed, no load speeds. We talked about the magnetizing current. And really quickly, what was that other component of current that we talked about? It's in your manual. It was the working current, the current that actually goes towards producing the torque to make everything move. So what I'm going to do now is I'm going to take this analog meter. It is currently set on the 25 volt scale, and I'm going to wire this up to analog input 1 and the common on the drive. And I want you to see that as I adjust this potentiometer, we go from 0 volts all the way up to 10 volts. And again, that's what scales, or that is the reference for the speed control for the motor that's being controlled by the VFD. So what we'll do is we'll run this, and we're at 0. If I increase this to 5 volts, which is halfway between 0 and 10 volts, we would expect to see a number close to 30 hertz, about halfway between 0 and 60, and we do. One other thing that I want you to notice here is I'm going to turn this all the way up, and what I'm going to do is I am going to wire up some actual pilot devices for us. So I'm going to take this positive 24 volts. I'm going to wire that up to my one side of my stop and jumper that 24 volts to the other side of my start push button. So I currently have 24 volts on the left hand side of both of these contacts. I'm going to wire our stop in to logic input 1. Hang on. I haven't changed our type of control yet to 3-wire control. So let's go over to I/O. TCC is type of control, and we're going to change it to 3C, which stands for 3-wire control. So now, notice how it says NST. What that means is we are currently giving the drive a stopping condition, because this is supposed to be wired to a normally closed pilot device. So when I actually send 24 volts to this logic input through this normally closed contact, notice how that stopping condition went away. If I push this push button, we're removing 24 volts, we go into a stopping condition again. A lot of people think this is a fault of the drive when they see that. It's simply that we don't have everything wired up yet. Logic input 2 is going to be start. So we are going to go to start. And what I want to show you here is a few things if I can. We've seen the 0 to 10 volts. So what I'm going to do now is take this meter and I'm going to change it to the 500 volt scale. And instead of connecting that up to analog input 1 in our common, I'm going to connect this up to the terminals that will show us the voltage that is currently on that DC bus. Now, every manufacturer is different with their filtering, but this is 208 volts in. Realistically right now, this building isn't being used very heavily. We're probably up to 215 to 220 volts just because there's no voltage drop or substantial voltage drop on our feeders. What do you think this voltage is going to be at if we assume maximum filtering and 215 to 220 going in? And if you recall, to get our peak voltage, which would be maximum filtering, we take our RMS value, multiply by √2. Why don't you go ahead and do that right now? And I am going to start our drive. Very important to check your polarity before you do this. Let's try again. Oh, there we are. So we are at, if I push start, just under 300 volts. And that should make sense with your calculation. If we try to break a load really quickly, then what will happen is that DC bus voltage is going to rise. I just want to show you one more thing before we finish, and that is when I push start, I want you to count how many seconds it takes. Maybe we'll get this out of the way. Count how many seconds it takes for this VFD to reach a speed of 60 hertz. And then how long it takes to stop. And both are 3 seconds because that's the factory default setting. That is very easily changed if we go into settings. Acceleration is the parameter for a ramp up time, so how long it takes to reach our desired set speed. And DEC, deceleration, is the parameter for the ramp down time. So what I'm going to do is I'm going to make my acceleration time 10 seconds, and I'm going to make my deacceleration time 1.5 seconds. So it'll be a little slower. We're not doing this with load on the motor, so we should be able to stop no problem here. So let's count again. Start. I'm a little fast on my counting, but 10 seconds and we're at 60 hertz. Now when I push stop, this should be much faster. 1.5 seconds. Some braking at the end. Well, everybody, I hope you've learned something about the Altivar 31. It's a relatively small, inexpensive drive, but it has quite a bit of capability built in. We'll talk to you soon. Bye for now.